Hi everyone, welcome back. This is Earth and Space Science 101, and we're going to continue to talk about geologic time today. So in the previous two lectures of this unit, we talked about relative and absolute age dating. Essentially, you can kind of think about these lectures as the rules in which we understand geologic time. They're the things that we use to sort of logic our way through understanding these layers of rock and the age of each of these individual layers. So that was sort of the backstory that we needed to be able to understand the rest of this unit, which is basically a chronology of Earth history. We're going to go back to the very beginning of time, at least on Earth, the very beginning of geologic time, which goes back to 4.54 billion years ago. And we're going to split up our discussion of geologic time into 4 lectures. The first thing that we're going to do is talk about our geologic time scale, and that'll give you a little bit of a reference into how we divide time. And you'll see sort of how we're going to divide up the 4.5 billion years of Earth history into 4 lectures. So that's where I want to start today, with the geologic time scale. The geologic timescale was originally constructed using relative age dating techniques. So it was constructed at a time where we didn't really know that much about how old the Earth was in exact number of years, or exactly how many years ago different events like the dinosaur extinction actually occurred. But we were able to put things in a sequence using relative age dating and be able to, at least sort of chronologically, tell the story or tell it in the correct sequence. So later on, once absolute age dating techniques using radiometric age dating were established, then we were able to finally go back and put numbers. And those numbers are always getting fine-tuned a little bit, but now we're able to confidently express the age of the Earth and the age of some of these events that have shaped the Earth. So this is one representation that you're seeing on your slide right now of the geologic timescale, but in this case it's expressed as a circle. So it's sort of analogous to expressing maybe 12 hours on a clock, where the first hour takes up 1/12 of the overall amount of space on the clock. This gives you a really good idea of the vast amounts of time that have occurred before humans were around on Earth, and even before large-scale life was around on Earth. Over 87% of all of geologic time occurred without large-scale organisms, either swimming around or roaming around on the Earth at the surface. So this is just one representation of the geologic timescale, and you can already see some of the names that are going to become really important later on, like the Hadean, the Archean, the Proterozoic. These are all names of eons of geologic time, so those are going to be really important to remember. You can also see some of the eras in the last little segment of time, kind of getting towards like a 10 or 11 o'clock on the clock analogy. Paleozoic, Mesozoic, and Cenozoic are all eras of an eon of time called the Phanerozoic. So another representation of the geologic time has it expressed a little bit more linearly, and as we go through each of these eons, and I give you a little bit of an insight into how they're named and what these names mean, this is maybe a better one to look at. Now, this one is heavily skewed, so it's not perfectly linear. It's heavily skewed towards the last eon of time, known as the Phanerozoic, so that one sort of looks bigger. Just remember that this isn't all to scale. The reason why that section of this particular time scale is bigger is because that's the part of the geologic time scale that we know the most about and we have the most accurate records for. The earlier eons of geologic time, we have less of a record, and we definitely know way less about the evolution of life during that time. So we're going to cover it a little bit more rapidly in the lectures. So the first thing that you have to understand about the geologic time scale is that the entire time scale, the entire 4.5 billion years of Earth history, is first subdivided into eons. So if you ever want to really exaggerate about how long something's taking, like you're sitting at home and you're watching this lecture and you're thinking, oh man, this is taking forever. Don't think about it as taking an epoch of time or an era. Think about it as taking an eon, right? An eon is the largest division of geologic time. There are 4 eons of Earth history. The first is the Hadean. That marks the first roughly 500 million years of Earth history. And Hadean traces its roots to ancient Greek. It's the same sort of root as the name Hades, who you might know as the god of the underworld. So that's the kind of imagery that I want you to sort of associate with the word Hadean, as sort of the hellish origins of Earth. This is a time when the entire surface of the Earth would have looked like most of our interpretation of what hell would look like. The entire surface is very, very hot, covered in lava. It's a very turbulent time during Earth history, and either extremely little or no life would have been able to survive on the Earth's surface at this time. The next eon of geologic time that occurs after the Hadean is called the Archean. And the root ARCH, that arc and Archean, always means really old. You know, when you're talking about archaeology, it refers to ancient humans on Earth and ancient human civilizations. So the Archean is really the early or ancient Earth. So this occurs after the Hadean, and so it occurs after the point in which the surface is cooled to the point where it's actually possible for life to start to evolve on the surface. So things start to get a little bit more like the Earth as we know it today. The third eon of time covers actually the largest division of time, and it's called the Proterozoic. So if you're talking about a prototype, you're talking about like an early model of something, like maybe a car. The Proterozoic is sort of like the early prototype of life on Earth. And so this is a division of geologic time in which many of the organisms that are still around today and the bacterial community and the microbial community, those really started to evolve and to reign on Earth during this time. We still, at this point, don't have any kind of macroscopic or large-scale life. So basically nothing bigger than a bacteria until you get to the very, very end of the Proterozoic. Now, the end of the word zoic, you're going to see a lot in these divisions of time because zoic means life. And so this is always going to refer to something that's going on with life in Earth history. So Proterozoic basically just means early life. And that spanned from 2.5 to roughly 500 million years ago. So this is 2 billion years of Earth history in this subdivision of time that we're calling the Proterozoic. Definitely the largest chunk of time of any of the eons. Finally, the last eon of geologic time, and the one that we are currently still in, is called the Phanerozoic. Now, you may have remembered a term from our discussion of minerals and rocks called phaneritic. It's a textural term that we associate with igneous rocks, and this means that that particular rock has large visible grains. So the root phaneros in anything always means visible. It means something that's large enough to be able to be seen with the naked eye without something like a microscope. So the Phanerozoic is this chunk of time in which large organisms, bigger than bacteria, were around on Earth. And it spans from 544 million years ago, or roughly about 500 million years ago, to now and extending into the future. So theoretically, for the distant future, we'll still be in this Phanerozoic eon. Now, you are responsible for the names of all of the eons of geologic time and the eras that we're going to continue talking about next. All these other divisions of time, even though I'm going to maybe talk about them in the lectures, you're not responsible for knowing in order. So things like the Cambrian, the Permian, the Cretaceous, these are all names of periods of geologic time, so it's not necessary for you to remember these. The next division of time that we're going to talk about, what eons are divided into, are called eras. And while there are eras of the earlier eons of geologic time, the Hadean, the Proterozoic, and the Archean, it's only going to be the eras of the Phanerozoic that you're responsible for knowing and that we're going to talk about in a lot of detail. So the 3 eras of the Phanerozoic are Paleozoic, Mesozoic, and Cenozoic. Now, all of those words, Phanerozoic, Paleozoic, Mesozoic, Cenozoic, all end with zoic, Z-O-I-C. And that always means life. So that gives you your first tip off right there of what these words mean. This is all going to refer to something going on with life. And it's our biggest concern when we go about dividing geologic time up into smaller and smaller chunks. It always tends to go back to what's going on with life at that particular time. So paleo, meso, and ceno are the only things that are dividing each of those terms for the individual eras up into smaller chunks. And that they literally translate into old, middle, and new. Paleozoic means old life. Mesozoic means middle life. And then Cenozoic means new life. So, once you actually break these words down into what they mean something just incredibly simple, and it's really easy to remember them this way. I would highly encourage you to try to remember these in the way that I've kind of described to you in this lecture here. It'll make a lot more sense on the test later on. So the Paleozoic covers, roughly around the first 300 million years of the Phanerozoic, from 544 million years ago to 250 million years ago. And this is a time when life is almost entirely going to be dominated by life in the oceans. And then towards the very end of the Paleozoic, life will evolve and then conquer the continents as well. In the Mesozoic, you have the reign of some of the most notorious organisms in the past on Earth, the dinosaurs, and they're, of course, going to go extinct at the end of the Mesozoic. Many of the species in the Paleozoic will have gone extinct by the end of the Paleozoic. So what's really sort of dividing up these eras of geologic time are big mass extinctions events, events where many, many species on Earth went extinct, and that paves the way for new organisms that did survive the extinction event to be able to evolve and to change and to flourish and dominate Earth in the wake of all of that destruction. The organisms that would eventually evolve and thrive after the dinosaur extinction were mammals, just like us. So the fact that we're around on Earth, that we're able to dominate on Earth, is largely due to the dinosaur extinction at the end of the Mesozoic. So we'll talk about that in a little bit more detail later. But suffice to say for now, this geologic timescale is going to be crucial to understand any of the lectures that follow today. This lecture that we're doing right now is going to be only the formation of the Earth and the first eon of geologic time, the Hadean. The next lecture that we're going to do is going to be the rest of the earlier eons of geologic time. That's the Archean and the Proterozoic. All three of the first eons of geologic time, the Hadean, the Archean, and the Proterozoic, are often combined into this sort of catch-all term. It's not an official term, but it helps us to kind of lump together all of that early Earth history into the term Precambrian. The Cambrian period is the first period within the Phanerozoic, and while you don't need to know the name Cambrian so much, sometimes it's useful to think about all of that time that came before the Cambrian as the Precambrian. So again, it's just a catch-all term for the first roughly 4 billion years of Earth history. So, like I said, this first lecture today, that's going to be just the geologic timescale that we've already discussed and the Hadean eon. The next one, lecture 23, is going to be all about the Archean and the Proterozoic. Lecture 24 is going to be just about the Paleozoic era because it's very dynamic. It's a very interesting era of geologic time. And then the final lecture is going to be on the rest of the Phanerozoic. That's going to be the Mesozoic and the Cenozoic eras. So we do have other subdivisions of time after eons and eras, but like I said, you don't need to memorize any of these terms. Eras are further subdivided into periods. For example, the periods of the Mesozoic are the Triassic, Jurassic, and Cretaceous. And while I might use those terms later on, it's not necessary for you to memorize them. And then those periods are sometimes divided into epochs. So a little bit later on, I'll talk about what epoch we are actually in right now. It's called the Holocene. But anything after eras, you're not responsible for memorizing. So the Precambrian, as I talked about before, is subdivided into the Hadean, Archean, and Proterozoic eons. It's just basically all of geologic time before large-scale life evolved on Earth, but there's a lot of physical stuff that's still interesting during that time. When we go back and we start to try to study the very, very early Earth history, it's extremely hard. When you're going back and you're studying something that's relatively recent in geologic time, like the dinosaur extinction, that's actually far easier because there's lots of records all over the Earth of the Cretaceous period. There's lots of rocks that are recorded from that time. But as you go back into earlier and earlier and earlier segments of Earth history, especially when you get older than 2 or 3 billion year old rock, it becomes increasingly rare to find rocks that have actually survived all of the tumultuous geological activity on Earth and survived up until this day. So trying to find the oldest materials on Earth and even the age of the Earth itself can be very, very difficult. But I'm going to give you a little bit more insight into why we use meteorites instead of material that has actually originated on Earth to come up with the age of the Earth when we do radiometric age dating. So when geochemists in particular go about studying rocks and determining their ages, a lot of those geochemists are always after the oldest rock on Earth or the oldest mineral on Earth. So the oldest rock and even the oldest mineral on Earth, those aren't going to show the full extent of Earth history. They're just going to be the oldest stuff that we've ever been able to find. The oldest rock on Earth was found in Canada. It's a little over 4 billion year old rock. And it's called the Acasta gneiss. It's not necessary for you to memorize that particular term. But it's important to remember that that's not the full age of the Earth. It's not 4.5 billion year old material. It's just the oldest stuff that we've ever been able to find. The oldest mineral is a little bit older. It's very much approaching the true age of the Earth. And it's a zircon, which is a mineral, from the Jack Hills area of Western Australia. It's 4.4 billion years old. Detrital zircons often contain uranium, and we can do the same sort of uranium-lead dating that we do to meteorites. So none of this stuff, the oldest rock, the oldest mineral on Earth, gives us the true actual age of the Earth at 4.5 billion years old. And again, the reason for this is because those oldest materials have largely been destroyed. In fact, even most of the stuff that's 4 or even 3.5 billion years old, most of that's been destroyed. Some very, very small little fragments still remain on Earth and allow us to actually date that material and get the oldest rock and the oldest mineral. But to get that true age of the Earth, we have to look for something extraterrestrial. So we think of the Earth as something that's sort of kind of isolated. We don't really think about it as having brethren or siblings out in space. But as it turns out, there's very strong evidence that the Earth did not form all by itself, all alone, all at one time. The Earth most likely formed with the other planets in the solar system all about the same time. It also formed with the formation of the sun itself. So all of this material that you could date from other planets, from other sources in our solar system, should all roughly still have that same maximum age. And when we do go about dating stuff from other planets, from samples that have been brought back from the moon, from primitive meteorites, we do get this consistent age of 4.5 billion years. Now, in the last lecture, we talked about the first of these primitive meteorites that were dated, the one that first gave us the true age of the Earth at 4.54 billion years old, and that was found in the Barringer crater, the famed meteor crater in southeast Arizona, and it's called the Canyon Diablo meteorite. But it's also important to remember that this isn't an isolated sample. This is these primitive meteorites have been dated from all over over Earth and still consistently give us the same answer of 4.54 billion years, plus or minus maybe a tenth of a billion years or so. So the reason why this works is because our planet, all of the other terrestrial planets, so that's Mercury, Venus, and Mars in addition to Earth, and even all of the other planets in the solar system, the so-called Jovian planets, that's Jupiter, Saturn, Uranus, and Neptune, and all the miscellaneous objects like Pluto and its icy brethren out in the outer solar system, comets, everything that's bound to the gravity of our sun was all formed roughly about the same time. So that formational process probably started a little bit before the maximum age of the Earth, so something around the order of maybe 4.6 billion years ago. All of these planets started to form. All of this planetary formation most likely formed as a result of the formation of our star. So this happens through a process called the nebular theory. The idea here is that in space, you have large areas of gas left over from dying stars. When stars run out of fuel, and this is hydrogen that fuels this process of fusion that allows stars to continue. It's essentially how our star is making energy today. Once those stars run out of fuel, they sort of go through this process where they explode and implode at the same time. The implosion of really big stars can lead to the formation of things called black holes that we discuss in a lot of detail in the 102 class. But when the explosion takes place, the gas from these stars gets vented out into space. It explodes, it rapidly expands out into space, and it makes these things called nebulas. A nebula is basically a big, gassy, dusty cloud in space. And that's a place where new stars form. So as this gas cools, it's drawn back inwards again by gravity. And the gravitational pull is going to pull all of that gas and this dust into this swirling disk of matter. And at the center of that disk, that's where temperatures are going to be high enough for fusion to start. And that's how stars form. Stars form from the collapse of the gas cloud of dead stars. So there's this wonderful sort of stellar reincarnation that occurs when new stars and new solar systems form. So the most important object within our solar system is not necessarily our planet itself, only for us. It's actually our sun. And the formation of our planet and the other planets within our solar system is sort of a side effect of the formation of that star. All of those little particles of dust that just happen to be part of that cloud then are going to collide together, and repeated collisions of millions or even billions of these tiny little particles are going to allow for the individual planets to form. In the outer solar system, where it's colder, it's possible for ice as well as rock and metal to be part of the planetary formation process. And then you form these planets that are able to accumulate giant atmospheres. So sometimes they're even referred to as gas giants, but we also know them as Jovian planets, planets like Jupiter. Our planet formed a little too close to the sun, so it ended up only being composed of rock and metal. And so we have a little small, comparatively to something like Jupiter, a small planet with a thin atmosphere around it that is at this perfect distance away from the sun for the stabilization of liquid water on the surface. And most likely because of that water, it's possible to sustain life on our planet. So that gives you a little bit of insight into how the planet itself came to be. And this wasn't an overnight process. This is a process that would have taken millions, possibly even hundreds of millions of years to shake out. But at the end of that whole process, you're left with this planet, Earth, and all of these other planets, Mercury, Venus, and Mars. It's even possible that there were some other rogue objects kind of floating around the inner solar system at this time. And that's going to be really important later on when we talk about where our moon might have originated from. So our moon is definitely a really big, important part of the story of the very, very early formation of the Earth itself. So we're going to get to that in just a little bit. But for now, we have this accumulation of all of these objects that are going to allow for the Earth itself to have formed. And so at this point, we'll say that the Earth has formed. But in a sense, it is still going to sort of have this process of planetary formation continue for at least 500 million years, and arguably even up to today. Even as long as any objects are still colliding with our planet, the planet's mass is growing. And so the planet itself is still sort of in this process of formation. And the very earliest chunk of geologic time, the first eon of Earth history called the Hadean, we're going to have this process of planetary formation still continuing. It still go on for roughly 500 million years. This period of Earth history is called the heavy bombardment period. And I like that term because it's telling you exactly what's going on. The Earth itself is being bombarded. So for not just years, but millions of years, roughly 500 million years, the Earth is going to still be orbiting around the sun, and the Earth itself will have sort of formed this relatively large object, but it's still clearing its orbit of all of this residual debris. All of these pieces of rock and metal out in space are still out there. And as soon as Earth sweeps by these objects in space, the gravity of the Earth is going to take these objects and cause those objects to move in towards Earth and collide with the surface. So it's a process not just of years, but of millions of years for Earth to have cleared its orbit from most of the objects that are going to be raining down on the surface. Now, 65 million years ago, or maybe kind of closer to 66 million years ago, when the dinosaur extinction happened, it was because a large asteroid collided with the Earth itself, and that knocked out life. Picture the kind of event that would have happened when the dinosaur extinction took place, happening every day, every hour for 500 million years. This raining down of these large chunks of rock and metal onto the Earth's surface. So the early Earth would have been a really horrible time to be around on Earth. You know, if you ever get a chance to get into a time machine and go into the past, if Doctor Who ever shows up in the TARDIS and ever decides he wants to take you back to some point in the early Earth history, don't go to the first 500 million years of Earth history. You will almost immediately get crushed by meteors raining down on the surface. It would be a really miserable time to be on Earth. And so this is what the Earth would be like for roughly 500 million years. It would just basically be a hellish surface. Every time one of those meteors collided with the surface, you would have had a melting of the surface, you would have had lava everywhere, and it was just sort of like this until the Earth was able to clear its orbit from all of this debris. Now, all of the accretions that occurred, all of these impacts that occurred that formed the Earth and continue to form the Earth, actually allow the Earth to still be hot today. The most important source of heat for the Earth's interior, and this is the source of heat that drives all of these processes like tectonics, then still drives them today, was the heat from the accretion. So every time two objects collided together to form some part of the early Earth, we still have some of that heat residing within the interior of our planet today. And objects in space, like the Earth itself, take a really long time to cool off. The space might be very, very cold, but it's also a vacuum. There is no gas in outer space. There's no material for the heat to actually transfer to. You know, so if you took, like, let's say a baked potato and stuck it out way out deep in space, it would actually take a really long time for it to cool off because there's nowhere for that heat to transfer to move to. And so the Earth itself would have taken a really long time to cool off and is still sort of theoretically in this process of cooling off today. Some of the other planets in our solar system, like Mars or even Mercury, are smaller. So they've already, in a sense, sort of cooled off. That's why those are either less or geologically active than our planet or have no geological activity. Maybe they did at some point in their past, but they don't have enough heat left to sustain that activity today. So that's one source of heat for the early Earth, is the heat from all of these impacts, the heat from the accretion, the heat from the process of forming the planet itself. Another source of heat that's also important for the early Earth is the convection and differentiation of the Earth's interior. And I know those are really big words, and they kind of tend to kind of just blow past your head. But what this means is the process of the density of the Earth's interior sort of shaking out and all of the heavy stuff sinking down to the center of the Earth, all the kind of more lightweight stuff floating back up to the surface, convection, which is a heat transfer process in which cold material sinks and then hot material rises up to the surface because of density. All of that motion of all of this material inside the interior of the Earth is going to generate heat. I like to kind of think about it as being sort of the difference between a lake freezing over winter and a river freezing. It's much easier for a lake to freeze because that water isn't moving, and so it cools off faster. A fast-moving river is going to be much harder for that river to freeze because that water is constantly moving, and the motion of the water itself is generating heat. And so the motion of material in the Earth's interior, sort of number 2 on this list, that's going to generate heat as well. Now, a very important source of heat for the Earth's interior, and one that is going to really pave the way to allowing us to understand geologic time and to understand how we absolute age date materials, is going to be radiometric decay. So if you remember back to earlier lectures when I was talking about Lord Kelvin and how he tried to calculate an age of the Earth and how it was an underestimate, his estimate was an underestimate because he didn't know about radioactivity. But these bits of material, they don't make up a substantial part of the Earth's interior, but these bits of material that are radioactive isotopes that are decaying over time, every time that decay process occurs, even in an individual atom, that releases heat. So when it happens over a large number of atoms, it actually adds up to a substantial source of heat for the interior of the Earth. And it has allowed the interior of the Earth to stay hotter for a longer period of time. In essence, the Earth's interior would have cooled off, tectonics would have shut down, and the Earth would have been uninhabitable were it not for radioactivity going on in the early Earth history. So this image here gives you a little bit of a sum up of all of these major events that we've talked about during the Hadean eon, the first 500 million years of Earth history. In the beginning, the Earth would have been basically this molten blob in space because of all of these impacts. Over millions of years, the surface would have cooled down. It would have been still consistently being bombarded by objects, but some differentiation of the Earth's interior would have been allowed to happen. The more dense iron and nickel would have kind of sunk down to the very core of the Earth. The more lightweight, silicon-rich rock would have floated back up to the surface, and then you would have had an Earth that was actually differentiated into crust, mantle, and core. And then later on, we'll form oceans and atmospheres. But before that happens, we have a very important point in Earth history, and that's when the moon came to be. So the first thing that I want to say about the moon and Earth is that it's a very underestimated part of the importance of Earth itself and how our planet is different than some of the other terrestrial planets in our solar system and some of the other terrestrial planets even outside of our solar system that are surrounding other stars. Very, very few planets have a moon that is as big as our moon is compared to the size of our planet. So while we are not the only planet to have a moon in our solar system, we are the only planet that has a moon that is as large as our planet. And this is really important for stabilizing the obliquity of the Earth itself, the axial tilt, which is in turn important for stabilizing our climate and making it possible for life to evolve and thrive on the surface of our planet. So the moon is very important. Mars has a couple of tiny little moons. They're called Phobos and Deimos, but they're so small in comparison to the size of the planet that you probably wouldn't even be able to see them very well from the planet's surface. Mercury and Venus don't have any moons at all. So our moon comparatively is very important, even as far as life is concerned on our planet. So our moon most likely formed from what we call a giant impact. it would have made the asteroid impact that led to the dinosaur extinction look very, very small in comparison. An object the size of Mars is thought to have collided with the early Earth at some point during the Hadean. We have very few remaining rocks from this time, and so it's really the presence of the moon itself and the fact that it's too large to be a captured object, like a captured asteroid, that gives us the most proof that this is probably how the moon itself formed. So we don't exactly know when this happened. It just most likely happened at some point during the Hadean. So this large object would have collided with the Earth itself and done so at a really oblique angle. Like you basically kind of have the Earth moving around the sun and the solar system, and then this rogue planet, this fifth terrestrial planet that some people call Orpheus. This planet would have almost missed Earth entirely and basically sort of just sideswipe it from a really, really low angle. And so what happened here is that during this impact, it probably knocked a lot of the mantle off of the early Earth, but allowed most of the core from the impacting object, the object that was roughly the size of Mars, to sink in and become part of the core of our planet. This would explain why Earth has a very large iron core compared to some of the other terrestrial planets. Earth is actually the largest of all the terrestrial planets, and it's probably as a result of the same impact that formed the moon. So then part of the mantle gets blasted off of the Earth, some of the mantle from and the crust of the impacting object, and all of this material would have been thrown out into space. If that material was thrown far enough out into space, it would not have come back to the planet. It would have orbited around the planet until the same sort of process that formed our planet orbiting around the sun would have happened to all of that ejected material. All that material would have coalesced and collided back together to form a moon. So then you have this moon that is then gravitationally bound to our planet because of the impact that allowed that moon to form in the first place. So we now have a moon, and we have an object that's actually stabilizing the Earth's orbit, which stabilizes our climate. And you can think of all of the evolution of life to come as partially dependent on this impact that formed the moon in the first place. So I've got lots of images and of animations of this colliding. This collision between these two objects that then formed the moon. But the big thing to kind of keep in mind here is that this collision would have increased the mass of the Earth itself. So Earth will have gotten much bigger as a result of this impact. That's the first big major point. The second big major point is that most of the mantle of that impacting object and some of the mantle from the Earth would have then formed the moon. So the moon really isn't that substantially different in composition than the Earth is, because some of the material from the Earth itself actually, in a sense, sort of birthed the moon. So now we have the moon, and we have something that's going to stabilize our climate a little bit. The other thing that's going to massively stabilize our climate is the formation of the oceans and the atmosphere, which most likely would have maybe started happening before the moon forming impact, but really started forming in a big way, at least after the impact, once the Earth's surface had a chance to cool down again. So some planets accumulate their atmosphere from, in a sense, sort of outside of themselves. Some planets are going to accumulate atmospheres from the same nebula that's going to allow for the star in that solar system to form. And that's certainly the case for gas giant planets like Jupiter and Saturn. Those planets have cores that were bigger to begin with, and so some of the gas from the formation of the star, our sun, is going to have been gravitationally bound to that planet instead. And so those planets are able to accumulate ridiculously large, very, very massive, thick atmospheres. In fact, those planet atmospheres are going to actually be more dense and more massive than the core of the planet itself. Our planet and other terrestrial planets are too small to have accumulated that same gas that from around the sun, because that gas is mainly hydrogen and helium. Our planet is not heavy enough to actually hold on to that hydrogen and helium unless those elements are sort of bonded together with other things, like hydrogen bonded with oxygen to make water. So our planet's atmosphere, instead of being taken from outside of our planet's surface and accumulated from outside and pulled in towards our planet, was probably, in a sense, sort of blown out from the interior of the planet. Those same rocks and metals that formed the meteorites that accumulated together to form our planet in the first place also contain things like water and carbon dioxide and nitrogen. And so once these materials have a chance to cool and solidify, the gas is going to escape from the rock itself. And where else can that gas go but outside the planet's surface? Then the gravity of our planet is going to be strong enough to hold on to these gases, and then they form our atmospheres. Now, note when I was listing all of these gases that these rocks contained that eventually became part of our planet's atmosphere, I didn't say anything about oxygen. Oxygen is not part of the original makeup of a planet's atmosphere, even though it's crucial to our lives today. Atmospheric oxygen currently makes up about 20% of our planet's atmosphere. But it wasn't there at all, even in trace amounts during the early Earth history. So the story of how oxygen comes to be on Earth is going to be a really important part of the story for the next lecture. So it wouldn't be until about 2.5 billion years ago that oxygen becomes part of the Earth's atmosphere. Instead, it's going to be mainly carbon dioxide, which is a very strong greenhouse gas, which would have kept conditions at the surface extremely hot, a little bit of water vapor, and things like nitrogen. And once the surface cooled at least enough so that some of that water vapor could condense, it is possible to eventually form oceans. So this process of cooling down our planet is going to continue slowly over time, cooling along the way. And eventually, some of that water vapor that escaped from the rocks is going to get cold enough to condense in the Earth's atmosphere. And what happens when water vapor in the atmosphere is cool enough to condense today is that it's going to rain. So this would have happened all throughout the atmosphere. So there would have been a global rainstorm, like that has never been seen on Earth since, and it would have rained for millions and millions of years. And eventually all of that water vapor would have been largely removed from the planet's atmosphere. Maybe a small residual amount would have remained, and instead all of that water is found on a liquid form on the planet's surface. And because we didn't have continents yet, that would come later as well, we have a planet that's entirely covered in water. The source of that water was most likely the meteorites that formed the Earth itself, especially a very specific type of meteorite called a carbonaceous chondrite. Those meteorites, and we can still study those meteorites today, those contain a large volume of water, something like possibly even 8% water. So that would have allowed that water vapor to then get out into the planet's atmosphere and then rain down onto the surface. So I'm going to cut to a little video that's going to show you where some of this water came from. And when we come back, we'll close out the lecture.
Unlike every other planet in our solar system, Earth's surface is 70% liquid water, which, while useful for life, is also kind of weird, because everything we know about how and when our planet formed says Earth's surface should be bone dry. The story goes like this. Our solar system formed from the collapse of a large cloud of dust and gas. The dense blob of gas at the center ignited to form the sun, which, as a young, unstable star, unleashed a fierce solar wind. Over time, this stream of charged particles pushed the remaining gas cloud farther and farther out, leaving only solid particles behind to clump together into rocks, planetesimals, and finally, the rocky planets of the inner solar system that we know today. And here's the problem. Water, in the form of ice, couldn't have been one of the solid particles that stuck around to form our planet, because the early inner solar system was far too hot for frozen water, and any water vapor would have been blasted away by the solar wind. So if Earth didn't start off with water, how did we end up with such splendid oceans? We know H2O wasn't manufactured here over the eons because natural processes like combustion, breathing, and photosynthesis create and destroy roughly equal amounts of water. And either way, the amounts in question are so minuscule that they can't account for the abundance of water on the planet. Since Earth's water was neither part of the original package nor manufactured here, it must have flown in from far away, on meteoroids or comets or other bodies originating in the outer solar system where they were far enough from the sun for frozen water to survive. The dirty ice balls we call comets are a logical candidate for the source of our water, but were ruled out when we discovered that they were far richer in heavy hydrogen than Earth water. Heavy hydrogen has a neutron as well as a proton in its nucleus, and for every million hydrogen atoms in Earth water, about 150 are heavy ones, while typical comet water has twice that many. These mismatched chemical signatures suggest that Earth's water couldn't have arrived on comets. It turns out that the most likely source for Earth's water is a type of meteorite called a carbonaceous chondrite. Chondrite is just the name given to the class of stony meteoroids that most commonly strike the Earth. But only the carbonaceous chondrites contain water, as well as lots of carbon if you couldn't tell from their name. They have water in them because they formed out beyond the sun's frost line, and what's more, their water has levels of heavy hydrogen similar to that of Earth water, strongly suggesting that these Earth crashers are the source of our ice caps, clouds, rivers, and oceans. And thus the water that turned our planet into a blue marble came quite literally out of the blue.
All right, so I hope you enjoyed that in this whole discussion of the first eon of geologic time, the Hadean. In the next lecture, we're going to go through the rest of the Precambrian eons. That's going to be the Archean and the Proterozoic. So we're going to finally solve the story of where did the oxygen come from and how did early life evolve. Until next time, keep rocking.